Welcome to the lecture series on process integration. This is module 6, lecture 4. The topic of this lecture is placement of heat engine, heat pump and reactors. We have seen that proper placement of heat engine or proper placement of any equipment with respect to pinch of a process GCC is important. We have seen the placement of distillation column. Similarly, we will see here how the placement of a heat engine, heat pump and reactors and what placement will help us to reduce the heat load on GCC or will make the equipment running free of cost. Now, a composite curve is shown like this. This is a TH diagram and this is the pinch. Now, the physical representation of process, here the hot utility temperature is there. This is the above pinch region, which is a heat sink because it needs heat from outside, and the below pinch region is a heat source. It needs cooling or it rejects heat into the cooling, and the Q is equal to 0 at this level, which is called pinch. So, heat QHU, which is the hot utility, comes to above pinch area. Here 0 heat passes through this pinch, and below the pinch this cold utility, to the cold utility it goes QCU, minimum cold utility, and this is minimum hot utility. So, whole process works under two temperature levels, that is hot utility temperature and cold utility temperature, and this is the above pinch region and this is the below pinch region. So, this is the physical representation of the process, and symbolic representation is this. This is pinch, this is sink, this is source, this is QHU and QCU. And once we know this representation, we will use this for our integration purpose. Now, let us take a steam turbine as heat engine. So, here from the HP steam, the steam comes, HP steam from this pipeline, and here we generate power and the LP stream goes. So, its pressure reduction takes place from HP stream to LP stream, and due to this pressure reduction, this steam turbine, which is a heat engine, gives us power. Now, the thermodynamic representation is like this. There are two temperature levels, T1, which is the source, the temperature level of this here, Q1 amount of heat flows to the engine, and Q2 amount of heat is rejected by the engine to the temperature level T2, which is this temperature level, where T1 is greater than T2, and in this process we get a work W. Now, the symbolic heat engine will look like this: T1, Q1, T2, Q2 and W. Now, this shows the diagram of a closed cycle heat pump. This is the evaporator where heat is picked up, and the amount of heat which is picked up is Q2, and during this evaporator, in this evaporator a refrigerant evaporates and we get refrigerant vapor here. This is compressed, and for compression we have to give some energy W, and then compressed vapor which is at a higher temperature goes to condenser, where it rejects Q1 heat, and the condenser is at a T1 temperature and evaporator is at T2 temperature. Then the vapor which is at a higher pressure condenses, becomes a liquid, then it is throttled through a valve where it undergoes pressure change, and then here we get a mixture of vapor and liquid at a lower temperature that goes to the evaporator, and the liquid part of the refrigerant evaporates by taking the heat, and again the cycle moves on. So, this is a closed cycle heat pump. Here T1 is greater than T2. That means, we are taking heat from a lower temperature and rejecting it at a higher temperature. This is against the natural flow of heat, which moves from a higher temperature to a lower temperature, and hence for this reverse flow of heat we have to spend energy for this purpose. Thermodynamic concept is this: it is a heat pump, picks up heat from a lower temperature level, rejects it at a higher temperature level. This is Q2 is sucked, Q1 is rejected, and for that we give work W, where T1 is greater than T2, and the symbolic is this: W goes into the system, we take up heat from T2, Q2 goes to the system, and Q1 is rejected at T1. So, we start first, we see the integration of heat engine. A heat engine accepts Q1 heat from a source at a temperature T1, rejects heat Q2 to a sink at a lower temperature T2, and generates work while doing so. So, from thermodynamics, W is equal to Q1 minus Q2, first law, and this W by Q1 is less than or equal to NC, this second law, where NC is 1 minus T2 by T1, this Carnot efficiency. So, if heat engine is not integrated with the process, then what we are consuming? Total heat input is QHU plus Q1, and total heat out is QCU plus Q2. So, this is the process. In the process, QHU is taken out in the sink and rejection is QCU. Similarly, the heat engine takes Q1 and rejects Q2. So, this is the consumption of utility when I take the process and heat engine simultaneously. Now, if I integrate this, then my this total heat input and total heat output should decrease, then only I get some profit out of it. So, let us see. So, this is my heat engine and this is my process. So, the heat input is QHU plus Q1, this plus this, and output is this plus this. Now, when I talk of placement of heat engine, so obviously placement can be done in 3 places of a GCC: above the pinch, below the pinch, and across the pinch. There is only 3 possible placements, and all these 3 possible placements we will see and check where it is profitable to place the heat engine. Now, this is a process, this is the heat engine. Now, if I am placing like this, I am taking Q1 and rejecting Q2 to this. If I do so, my hot utility decreases by QHU minus Q2. So, heat engine integrated with the above pinch, my total heat in is QHU minus Q2 plus Q1, and which is nothing but QHU plus W, because Q1 minus Q2 is W, and total heat out is QCU. When the engine exhaust Q2 is hotter than the pinch temperature and above the pinch, the engine takes Q1 and rejects Q2, which is equal to Q1 minus W into the sink. Thus, the integrated system uses W units of additional heat in excess of the process requirement. It produces an equal amount of work also at the same time. So, heat is converted to shaft work at almost efficiency of 100% because of the integration. The heat Q2 rejected by the engine substitutes an equal amount of hot utility, and the hot utility requirement of the process reduces to QHU minus Q2. Now, we see across the pinch. Heat engine integrated across the pinch. When the engine exhaust is colder than the pinch temperature and the engine is across the pinch, the engine rejects Q2 amount of heat into the process source. So, it is rejecting Q2 amount of heat into this process source, which is below pinch. This heat simply cascades through the below pinch region and increases the cold utility requirement. So, it has increased the cold utility requirement. Now, if I am integrating it below the pinch, the heat is integrated below the pinch, I am taking Q1 heat from this below the pinch and rejecting it into the cold water. So, the demand of the cold utility for the process is QCU minus Q1. So, this is QCU minus W. Below the pinch, the engine absorbs Q1 from the process source and thereby reduces the cold utility demand. So, after seeing this, let us see what is happening. Without integration, my total hot utility was QHU plus Q1, total cold utility was QCU plus Q2. Now, above the pinch, when I am integrating it, it becomes QHU minus Q2 plus Q1 is equal to QHU W, and the cold utility remains same. When across the pinch I operate, this becomes QHU plus Q1, QCU plus Q2, the same as without integration. And when the below pinch I am doing, the QHU remains same, but your cold utility becomes QCU minus W. So, now the final conclusion is that if I am putting up above the pinch, it is a proper placement, though it is not benefiting me very much, but it is decreasing the amount because Q1 will be more than W. The below pinch, it is proper placement because it is decreasing the cold utility by W amount, but if I am putting it across the pinch, this is a improper placement. So, whenever I will try to integrate my heat engine with a process, it will be either above the pinch or below the pinch, and it will never be across the pinch. So, this conclusion we draw by integration. Now, let us see the heat pumps. After finishing the integration part of the heat engines with process GCC, let us take the case of heat pumps and its appropriate placement. So, symbolically the heat pump is shown like this and the process is also shown on the right hand side. So, heat available is Q 1, heat in is Q H U, heat required is Q 2 and heat out is Q C U. So, here heat is pumped, Q 2 amount of heat is pumped by using W amount of work and it converts into Q 1. So, this heat is available and this needs to be pumped from a lower temperature level. Now, a heat pump is a heat engine operating in reverse. This we know. It accepts Q 2 heat at temperature T 2 at a lower temperature, which is rejects Q 1 at a higher temperature T 1, and therefore, consumes work which is equal to W, because it is against the natural flow of heat. From thermodynamics, W is equal to Q 1 minus Q 2, first law. Second law, W by Q 1 is greater or equal to N C, N C is this 1 minus T 2 by T 1, and the equation for rear reversible heat pump is this, where N mechanical efficiency is this need 0 to 1. There is a concept of COP here. Now, let us take the placement of heat pump across the pinch. So, when I talk about the placement of the heat pump vis-a-vis the pinch, then it can be above the pinch, it can be below the pinch, or it can be across the pinch. So, there are 3 places for placement and we have to check all these 3 places and see where the placement is beneficial and where we should not place the heat pump. Now, we see the heat pump integrated across the pinch. So, what we are doing here, I am injecting heat Q 1 to this sink and taking Q 2 heat from here, injecting Q 1 heat to the sink, and to transfer the heat I am working giving work equal to W. So, when I do so, the hot utility requirement reduces from Q H U to Q H U minus Q 1, and the cold utility requirements also reduced Q C U minus Q 2, and this is expected because at the source heat is available, extra heat is available, which will otherwise go to the cold utility. So, if I take up some heat from here, so consumption of cold utility will decrease. Similarly, sink needs heat, if I supply from outside, it will decrease the hot utility requirement, and this is what we see here. So, heat in is Q H U minus Q 1 is equal to Q H U minus Q 2 minus W, and heat out is Q C U minus Q 2. The heat pump placed across the pinch takes heat Q 2 from the process source below the pinch and rejects heat Q 1 to the processing above the pinch. The work input W leads to a reduction of hot utility as well as the cold utility. So, we are spending W amount of work but while doing so we are reducing the hot utility and cold utility requirement. After integration, hot utility demand drops to QHU minus Q2 minus W and cold utility demand drops to QCU minus Q2. Now, heat pump integrated above the pinch. So, if I integrate it above the pinch, so at a particular temperature level I pick up, I send the heat, reject the heat at this temperature level. At the bottom temperature level I pick up the heat Q2 at a T2 temperature level and reject it at a T1 temperature level, where T1 is greater than T2, and these are the temperature levels. So, while doing so, my hot utility requirement is QHU minus W and QCU remain same. Heat in is QHU minus W and heat out is QCU. So, hot utility gets reduced by W units. W units of work also added for net energy saving. So, I am utilizing W amount of work and I am getting the reduction in QHU the same amount. Q2 units of heat circulated in the loop, from this to this area Q2 amount of heat is being circulated. Work W is added to the heat source. So, no special gain. So, whatever I am investing, the same I am getting. So, no special gain. If a heat pump is integrated below the pinch, so here at a lower temperature level I am picking up Q2 amount of heat and then pumping it at a higher temperature level T1 and spending W amount of work. So, heat in is QHU, this is remains unchanged, heat out is QCU plus Q1 minus Q2 is equal to QCU plus W. So, hot utility remains as it is, W units of work also added, Q2 units of heat circulated in the loop below pinch and W work W is added to the heat source, thus cold utility increased by W amount. Let us now see the conclusion part of the heat pump integration with the process. Now, without integration, the heat available with the heat pump is Q1, that means it is able to push Q1 heat to the surrounding, and heat required for the heat pump is Q2, that means it picks up Q2 heat and sends Q1 heat to the surrounding. And if you see the process, hot utility requirement for the process is QHU and the cold utility requirement is QCU. So, when we integrate the heat pump above the pinch, the hot utility requirement becomes QHU minus W and the cold utility requirement remains unchanged, that is QCU. However, we are utilizing W power to pump the heat Q2 from a lower temperature and rejecting it with Q1 at a higher temperature. So, practically no gain, because we are investing W work and we are reducing the heat by W. So, no gain. But if you see for the across the pinch, when we integrate the heat pump across the pinch, then my hot utility requirement comes down and this is now QHU minus Q2 minus W, substantial reduction in hot utility, and then QCU also reduces, that is cold utility requirement, and it becomes QCU minus Q2. So, here we get a gain, that means hot utility reduction is there and cold utility reduction is there. Below the pinch, if you see the scenario, the hot utility remains the same, but the cold utility increases by W amount. So, here also below the pinch we are a loser and we are not a gainer, and hence the final conclusion will be that above the pinch improper placement, that means do not place heat pumps above the pinch. Across the pinch proper placement, because it reduces the hot utility and cold utility, and below the pinch again improper placement, that means do not place heat pump below the pinch. So, the only place where heat pump will profitably work is across the pinch. Now, let us take the reactor, the placement of the reactor. The reactor is the heart of a process and its operating conditions are fixed during the development of process flow sheet based on maximum yield, selectivity, catalyst life and market driven product quality. Thus, designers and operators are often unwilling to make major changes in the reaction conditions. Because of this, direct heat integration of reactors with process stream is hardly done. Under this backdrop, pinch analysis may propose acceptable refinements which may allow the process to integrate better. Now, the heat integration characters of the reactors can be divided into three parts: decomposition, modeling and thermodynamics. In the decomposition of the reactor, it is energy functions, that is enthalpy change of the reaction, transfer of this enthalpy from to the fluid, interchange of energy between fluids entering the reactor at different temperatures and exchange with the surroundings are considered separately. The reaction enthalpy is presented at a reactor profile and other energy functions are a process profile. Now, the proper placement of reactor depends upon type of reactors. Generally, reactors are of two types: exothermic, endothermic. Heat duty on the heating cooling medium of a reactor can be written like this: Q reactor is equal to minus delta H streams plus delta H reactants, and Q react is the reactor heating or cooling requirement, delta H streams is enthalpy change between the feed and product streams, and delta H react is reaction enthalpy negative in the case of exothermic reactions. Now, integration of reactors with background process. If I have a exothermic reaction, then integration if I do above the pinch, then it is beneficial, because exothermic reactor has got large amount of energy available with it and needs cooling. So, that heat can be put into this to decrease the hot utility demand above the pinch. Now, if I put this below the pinch, then the cold utility demand increases, which is not an acceptable fact. So, the proper placement is above the pinch if it is a exothermic reactor. For endothermic reactors, it will be reverse. If I pick up it, if I integrate it above the pinch, then it will take heat from here and this is heat deficient. So, my hot utility requirement will increase, which is not acceptable, and if is integrate it below the pinch, here extra heat is available which can go to the endothermic reactor. So, it will reduce the cold utility amount of the process. So, this is a acceptable fact. So, proper placement is this: if it is a endothermic reactor below the pinch, if it is a exothermic reactor above the pinch. So, these are the references. Thank you.